There is a particular kind of fear that only a few people in history have ever felt. The fear of having discovered something true that you desperately wish were not. Just over a century ago, a man stood at the front of a quiet lecture hall and, in a flat and tired voice, read out an equation that would shatter everything humanity believed about reality. Almost no one in the room understood what had just happened. He did. He called what he had done an act of desperation, and then, instead of celebrating, he went home and began the strangest project of his life. A 10-year effort to prove his own greatest discovery was a mistake. He was not being modest. He was afraid, because he had seen before anyone else alive that the universe was far stranger, and far less certain than any human being was ready to accept. What could a single man possibly find that would make him spend his remaining years trying to unsay it? Make yourself comfortable, subscribe if you haven't already, and stick around, because the closer we follow his fear, the more clearly you will see exactly what he was so desperate to bury. Let's begin. Part 1. The Man Who Came to Defend Physics. There is a particular kind of person who breaks the world by accident, and almost always it is the person who is trying hardest to keep it intact. Max Planck was that person. He did not set out to start a revolution. He set out to prevent one, and by the time he understood what he had done, it was already too late to take it back, though he would spend the rest of his life trying. To understand why this story matters, you have to understand the man at the centre of it, because nothing about him fits the picture you might have in your head of the scientist who cracks reality open. We tend to imagine those people as rebels, as outsiders, as restless minds hammering at the doors of accepted wisdom. Planck was the opposite of all of that. He was careful. He was formal. He wore dark suits and kept regular hours and believed, with something close to religious conviction, that the universe was orderly, lawful, and ultimately knowable all the way down. He loved music, played the piano beautifully, and considered becoming a professional musician before physics pulled him in. He was, in almost every way, a conservative man who wanted the rules to hold. When Planck was a young student, sometime around 1874, he went to one of his professors, a physicist named Philip von Jolly, and asked for advice about whether to devote his life to the study of physics, and von Jolly told him not to bother. The professor explained in so many words that physics was essentially finished. The great discoveries had all been made, the foundations were laid, the cathedral was built, and all that remained for the next generation was to go around with a cloth and polish the corners, measuring known quantities to a few more decimal places. There was, the older man said, nothing important left to find. Now, sit with how strange that is for a moment, because we are standing at the very end of the 1800s, and the most respected voices in science genuinely believed they had nearly completed the job. They had Newton's laws, which described how objects move with such precision that astronomers could predict the positions of planets years in advance. They had the laws of thermodynamics, which governed heat and energy and seemed to apply everywhere without exception. They had James Clerk Maxwell's equations, which had unified electricity, magnetism, and light into a single elegant framework. The machinery of the universe, as they understood it, ran like a perfect clock. Wind it up, set it going, and everything that followed was determined, predictable, smooth. There were no jumps in this picture, no gaps, no surprises. Nature, they were certain, did not make leaps. And here is the part that tells you everything about Planck. When his professor told him physics was a dead end, Planck did not change course. He chose it anyway. But listen to his reason, because it is the key to the whole story. He said he had no desire to discover new worlds. He only wanted to understand the foundations that already existed, to grasp the deepest principles of the physics he already loved. He wanted to go to the bottom of the clock and admire how perfectly it had been built. That was his ambition. Not to overthrow the cathedral, but to kneel inside it and study the stones. This matters because it means the man who was about to shatter classical physics was, in his own mind, its most devoted defender. He was not looking for cracks. He was looking for bedrock. He wanted to find the place where the laws bottomed out into something absolute and unchanging, and he believed with his whole being that such a place existed. The tragedy and the wonder of Max Planck is that he went looking for the most solid ground in all of physics, and instead he found the exact spot where the ground gives way. For years he circled the questions that fascinated him most, and they were not glamorous questions. Planck was drawn to thermodynamics, the science of heat and energy, and the strange one-way nature of time that it implied. He was especially captivated by something called the second law of thermodynamics, the principle that heat always flows from hot things to cold things, that disorder always tends to increase, that you can unscramble nothing, and that the arrow of time points stubbornly in one direction. To most people this sounds like dry bookkeeping. To Planck it was almost sacred. He believed the second law was not merely usually true, not merely true on average, but absolutely true, a law without exceptions, woven into the deepest fabric of reality. He would defend that belief fiercely, and it is the first of his cherished convictions that the universe was going to take away from him. You need to understand how personal this was for him, because it explains the resistance that comes later. There was another physicist of the era, an Austrian named Ludwig Boltzmann, who had a radically different idea about the second law. Boltzmann argued that the law was not absolute at all. It was statistical. Heat flows from hot to cold not because some iron rule forbids the reverse, but simply because there are overwhelmingly more ways for energy to spread out than to concentrate. So spreading out is what almost always happens, the way a shuffled deck almost never comes out sorted. In Boltzmann's universe, the orderly behaviour we see is just the most probable behaviour, and in principle, given enough time, anything could happen. Heat could, with astronomically tiny odds, flow the wrong way. Planck hated this idea. He found it almost offensive. To say that the most fundamental law of nature was merely a matter of probability felt to him like surrendering the certainty that made physics physics. If the laws were only statistical, then the clockwork was not perfect after all. There was slack in the gears, a whisper of chance hiding in the foundations, and so for much of his early career Planck stood against Boltzmann's statistical reasoning, holding the line for a universe of absolutes. Remember that, because the cruelty of what is coming is that to solve the problem that would make him famous, Planck would be forced to pick up the very tool he had spent years rejecting, the statistical method of the man he had argued against, and use it to break his own deepest belief. So picture him now, this careful, conservative man, somewhere in the 1890s, established and respected, a professor in Berlin, the inheritor of a grand tradition that everyone agreed was nearly complete. He has no idea that he is about to walk into the one problem that the perfect clockwork cannot solve. He does not know that the smooth, continuous, deterministic universe he loves has a flaw in it, a single thread that, when pulled, unravels everything. He thinks he's going to spend his life polishing the corners, just as his professor predicted. He thinks the cathedral is finished. And yet there is a clue, even this early, to why he of all people would be the one to find the flaw. The very trait that made Planck conservative also made him relentless. He was not satisfied with physics that merely worked. He needed to understand why it worked, all the way down, with no loose ends and no comfortable hand-waving. A more casual thinker might have looked at the glow of a warm object, shrugged, and trusted that the established laws would sort it out eventually. Planck could not do that. His need for the foundations to be truly solid meant he could not rest until he had personally verified that they were, and that compulsion would march him straight into the one corner of physics where the foundations were not solid at all. This is the quiet paradox at the centre of his life. The people most likely to discover that a belief is false are often the ones who hold it most sincerely, because only they care enough to test it to destruction. A skeptic might have suspected the old physics had limits and simply moved on. Planck believed in it too completely to leave it half-examined, and so he became the instrument of its undoing. His loyalty was the lever that pried the door open. He loved the cathedral enough to inspect every stone, and in inspecting them, he found the crack that no one who loved it less would ever have looked closely enough to see. And the strange thing, the thing that makes this more than a history lesson, is that the problem waiting for him would not arrive disguised as a great cosmic mystery. It would not come from the stars or the depths of the atom or the edge of the universe. It would come from something almost insultingly ordinary. It would come from the glow inside an oven, from the colour of heat itself, from a question so mundane that it was being studied not by dreamers, but by engineers trying to build better light bulbs. That is where the trouble was hiding, not in the heavens, but in a furnace. And the man who was about to look into that furnace and see something that would terrify him for the rest of his days had no idea, as the old century wound down, that he was already standing at the edge of everything he believed. He thought he was guarding the door. He did not yet know he was about to open it. Because before Planck could find his answer, he first had to confront the question that no one in that confident, self-satisfied age could crack. The question glowing quietly inside every fire, every forge, every heated piece of metal on Earth. And the closer anyone looked at that ordinary glow, the more impossible it became. Part 2. The light inside the oven. Think about the last time you watched something heat up until it began to glow. Maybe it was the coil of an electric stove, sliding from black to a dull red. Maybe it was a campfire poker left too long in the flames, or the filament of an old bulb, or footage of molten steel pouring in a foundry. Whatever it was, you already know the sequence, even if you have never thought about why it happens. Cold metal is dark. Warm it, and it glows a dim red. Heat it more, and the red brightens toward orange, then yellow. Push it hotter still, and the glow turns white, and then, at the most extreme temperatures, it shades toward blue. The colour of a glowing object tells you its temperature. This is why a blacksmith can judge the heat of iron by eye, and why astronomers can tell you that a red star is cooler than a blue one. The light in the oven is a thermometer written in colour. This was the quiet mystery sitting at the centre of physics as the 19th century closed, and what makes it so beautiful as a story is how ordinary it looked. Nobody approached this problem expecting it to break the universe. They approached it because it was useful. Germany at the time was building a powerful electrical and lighting industry, and there was real money in understanding exactly how hot objects radiate light. If you wanted to design a better light bulb, a brighter and more efficient filament, you needed to know precisely how much light of each colour a glowing object gives off at each temperature. So this was, in the most literal sense, an engineering question. It was about making better lamps. And to answer it, physicists built a very particular kind of object and gave it a slightly forbidding name. They called it a blackbody. Let me tell you what a blackbody actually is, because the name is misleading, and the reality is more elegant than it sounds. A perfect blackbody is an idealized object that absorbs every single ray of light that falls on it, reflecting nothing at all, which is why it is called black. But here is the clever part. An object that perfectly absorbs all light is also, when heated, a perfect emitter of light. It glows in the purest possible way, with a spectrum that depends on nothing except its temperature. Not its shape, not its material, not what it is made of, only how hot it is. So if you could build a perfect blackbody and heat it to a known temperature, the light coming out of it would be a kind of universal signature, the same for everyone, everywhere, a pure expression of heat itself. In practice, you cannot carve a perfect blackbody out of any material, so the physicists did something wonderfully simple. They built a hollow cavity, a closed box or a closed oven, and they drilled one tiny hole in the side of it. Then they heated the whole thing to a precise temperature. Any light that wandered in through that little hole would bounce around inside, absorbed and re-emitted by the walls again and again, until it had completely forgotten where it came from, and had blended into the pure radiation of the cavity's temperature. The light that leaked back out of the hole was, as near as anyone could manage, perfect black-body radiation. That small, bright opening glowing with the colour of pure heat is the glow in the oven. Hold on to that image, because that humble little hole is where the entire history of modern physics turns. There is a lesson hiding in the ordinariness of this setup, and it is one of the quiet themes of all of science. The places where reality cracks open are almost never the places we expect. We imagine that the great secrets must be locked away somewhere dramatic, at the bottom of the sea, in the core of a star, at the beginning of time. But again and again, the universe has hidden its most important truths inside things so familiar that we walk past them every day without a second thought. An apple falling from a tree, a compass needle swinging toward the north, the glow of a warm piece of iron. These are not exotic phenomena. They are the most common sights imaginable, and yet each one, looked at closely enough, turned out to contain a doorway into a deeper layer of the world. The glow in the oven belongs to that family of humble doorways. For thousands of years, human beings had watched metal change colour as it heated, had judged the readiness of a forge by the shade of the iron, had stared into fires and seen red soften into orange and white, without ever suspecting that this everyday spectacle held a contradiction capable of toppling the proudest physics ever built. The information was always there, pouring out of every flame, free for anyone to read. What was missing was not the phenomenon. It was a mind prepared to be troubled by it, a mind unwilling to accept that the warm light it had seen 10,000 times was something it did not actually understand. Most people see a fire and feel comfort. A few people see a fire and feel a question they cannot put down. Now, the experimentalists were very good at their jobs. In laboratories in Berlin, men with names like Lummer, Pringsheim, Rubens and Kurlbaum built these heated cavities and measured, with extraordinary care, exactly how much energy came out at each wavelength, at each colour, for a whole range of temperatures. They produced beautiful, clean curves. For any given temperature, if you plotted the brightness of the radiation against its wavelength, you got a smooth hump. At long wavelengths, out in the infrared, the energy was low. As you moved to shorter wavelengths, the energy climbed, rose to a peak at some particular colour that depended on the temperature, and then fell away again toward the short wavelength ultraviolet end. The hotter the cavity, the higher the peak, and the more the peak shifted toward the blue. What is quietly remarkable about these curves is that they are the same for everyone and everything. This is the property that made the black body such a pure object of study, and it is worth dwelling on because it points at something universal. The shape of that glow does not care what the cavity is made of, whether its walls are iron or copper or clay. It does not care about the size of the box or the shape of the hole. It depends on temperature and temperature alone. Two cavities at the same temperature, built by different people on different continents out of different materials, will glow with exactly the same spectrum of colours. The radiation has forgotten everything about its origins except how hot it is. That universality is a hint, the kind of hint nature drops when something fundamental is hiding nearby. Whenever a phenomenon stops depending on the particular details of how it was made, and starts depending only on a single fundamental quantity like temperature, physicists learn to pay attention, because it usually means they have stumbled onto a law that reaches beneath the surface of things. The black body glow was telling everyone who studied it that it was not really about furnaces or filaments or any specific object at all. It was about the relationship between heat, light, and matter in its most stripped-down form. The experimentalists were not measuring a property of their equipment. They were measuring a property of the universe, and the universe was about to prove that no one yet understood it. This is exactly the everyday pattern we started with, the shift from red to white to blue as things get hotter, now captured as precise data, accurate to many decimal places. So the experiment was solved. The measurements were sitting right there, clean and reliable. And that is when the real trouble began, because measuring a thing and explaining a thing are two completely different acts. The experimentalists had the curve. What nobody had was a theory, a piece of physics derived from first principles that could reproduce that curve and explain why nature should glow in exactly that way. And this was supposed to be the easy part. This was supposed to be precisely the kind of corner polishing that Planck's old professor had described, a known phenomenon waiting to be tidied up with the established laws. Take the trusted physics of the 19th century, the thermodynamics and the electromagnetism that everyone agreed were nearly complete. Apply it to this glowing cavity, and out should come the curve the experiments had already revealed, except it did not. When the finest minds in Europe took the perfect, trusted, beautiful machinery of classical physics and pointed it at the glow in the oven, the machinery gave the wrong answer. Not slightly wrong, not wrong in the third decimal place, catastrophically, absurdly, impossibly wrong, in a way that should have been impossible for laws that worked flawlessly everywhere else. The very physics that could predict the motion of planets and the behaviour of engines, the physics that had earned the right to call itself nearly finished, could not explain the colour of a warm piece of metal, and the reason it failed is one of the most beautiful and unsettling things in all of science, because the failure was not a small mistake that could be patched. It was the trusted theory, applied correctly, marching with perfect logic straight off a cliff. Every step in the reasoning was sound. Each piece of physics was one that everyone accepted. And yet the conclusion they led to was a prediction so insane that it would later be given a name worthy of a disaster film. They would call it the ultraviolet catastrophe. And it was not just a problem about light bulbs anymore. It was the universe quietly announcing that something in the foundations was broken. Planck did not rush to this problem at first. He came to it gradually, drawn in by his love of thermodynamics and the second law, sensing that the radiation in that cavity had something to teach him about the absolute principles he treasured. He thought, at the start, that this was an opportunity to demonstrate the perfection of the laws he loved, to show that classical physics, properly applied, could capture even this. He believed he was walking toward a triumph. He had no idea he was walking toward the cliff, and to understand the size of the fall that was waiting for him, we have to look closely at exactly how and why the most trusted physics in the world predicted that every warm object in existence should be pouring out an infinite blaze of light. Part 3. The place where the numbers broke. To feel why the glow in the oven broke physics, you have to picture what the old theory imagined was happening inside that heated cavity. The walls of the oven are made of atoms, and those atoms jiggle when they are warm. In the language of 19th century physics, you could think of the walls as filled with countless tiny oscillators, little vibrating charges, each able to ring at its own frequency, like an enormous orchestra of microscopic strings. A string that vibrates slowly gives off low-frequency, long-wavelength light out toward the red and the infrared. A string that vibrates quickly gives off high-frequency, short-wavelength light toward the blue and the ultraviolet. The radiation filling the cavity is the combined song of all these oscillators, every possible note sounding at once. Now, classical physics had a very clear rule about how energy gets shared out among all these vibrating modes, and it was one of the proudest results of the era. It was called the equipartition of energy, and the idea was democratic and clean. When a system settles into equilibrium at a given temperature, energy distributes itself equally among every available way of moving. Every oscillator, every mode of vibration, gets, on average, the same share of energy as every other. It didn't matter whether a mode vibrated slowly or quickly. Each one was entitled to its equal portion. This principle worked wonderfully in case after case. It explained the behaviour of gases. It explained the heat capacities of many materials. It was trusted, tested, and beloved. So far, this sounds harmless, even fair. The trouble appears the moment you start counting how many modes there actually are at each frequency, because the modes are not distributed evenly across the range of colours. As you go to higher and higher frequencies, toward the blue and then the ultraviolet and beyond, the number of possible vibration modes does not stay constant. It grows, and it does not grow gently. The number of available modes increases with the square of the frequency, which means that for every step you take toward the short wavelength end of the spectrum, you find dramatically more ways for the cavity to vibrate. There are vastly more high-frequency modes than low-frequency ones, and the gap keeps widening without limit as you climb toward the ultraviolet. Put those two trusted ideas together and watch what happens. Every mode gets an equal share of energy. That is the first idea. And the number of modes grows without bound as you go to higher frequencies. That is the second. Multiply them. If each of an ever-increasing number of modes gets the same fixed portion of energy, then the total energy radiated at high frequencies should climb higher and higher with no ceiling at all. The short wavelength end of the spectrum should blaze brighter and brighter, and because there is no upper limit to how high frequencies can go, the total energy should not just be large, it should be infinite. Let that conclusion land, because it is genuinely deranged. Classical physics, applied with perfect honesty, predicts that any object warmer than its surroundings, anything at all with a temperature, should be radiating an infinite amount of energy, concentrated overwhelmingly in the ultraviolet and beyond. It says that the warm cup of tea beside you should be flooding the room with a lethal, unbounded blast of ultraviolet light and X-rays. It says that every fireplace is, in principle, an infinite bomb. It says you cannot sit near a campfire without being instantly vaporized by an unlimited torrent of high-frequency radiation. This is the prediction that the most successful physics in human history actually makes about the simple act of something being warm. And of course, none of that is true. You can sit by a fire and feel nothing worse than pleasant warmth and a soft red and orange glow. The real radiation curve, the one the experimentalists had measured so carefully, does exactly the opposite of what the theory demands. Instead of rising forever toward the ultraviolet, the measured energy rises to a peak, and then falls, dropping back toward zero at the high-frequency end. Nature, in reality, switches off the ultraviolet. It is worth asking why nature switches off the high frequencies, because the answer, once you know it, is the whole secret in a single sentence. In the classical picture, every vibration mode is entitled to its full share of energy for free, no matter how high its frequency, and that is what leads to the runaway blaze. But if energy comes only in packets whose size grows with frequency, then the high-frequency modes face a kind of admission price that climbs higher and higher. To get even a single packet of energy into a very high-frequency mode, you would need to pay a very large lump of energy all at once, and at any ordinary temperature there simply is not enough energy lying around to afford it. So the high-frequency modes mostly sit empty, priced out, unable to gather the minimum lump required to participate. The ultraviolet goes dark not because nature forbids it, but because, at everyday temperatures, the cost of admission is more than the universe can pay. That single idea, that the high notes cost more, is the quiet hinge on which the catastrophe is resolved. It explains why the glow peaks and then falls instead of climbing forever. It explains why hotter objects, which have more energy to spend, can afford to push their glow toward the blue, lighting up modes that cooler objects cannot reach. The whole shape of the curve, the gentle rise and the graceful fall, follows from the simple rule that energy comes in lumps and the lumps grow with frequency. But no one knew that yet, standing at the cliff in 1900. All they had was the impossible infinity and the gentle, finite glow that mocked it, and the dawning sense that one of their most trusted laws was about to be revealed as a beautiful mistake. The theory says the high frequencies should dominate everything. The world says the high frequencies quietly go silent. The gap between those two statements is not a rounding error. It is the difference between a finite, livable universe and an impossible one. A physicist named Paul Ehrenfest would later give this disaster its unforgettable name. He called it the ultraviolet catastrophe, and the word catastrophe is not poetic exaggeration. It is a precise description of what the equations do. They diverge. They run off to infinity. They detonate at the blue end of the spectrum. and the deepest horror of it, for anyone who loved classical physics the way Planck did, was that you could not point to a single wrong step in the reasoning. Equipartition was correct as far as anyone knew. The counting of the modes was correct. The electromagnetism was correct. Every individual piece was a trusted, tested law. And yet, assembled together and aimed at the humblest glowing object, they produced a monstrous, infinite lie. This is what it actually means for a foundation to crack. It is not that one obviously faulty idea gets exposed. It is that a set of separately reasonable, separately verified ideas combine to produce an impossibility, which means that at least one of those cherished ideas somewhere has to be quietly, fundamentally false, even though each of them seems beyond question. Somebody was going to have to walk into that beautiful, trusted machinery and break a piece of it on purpose. Somebody was going to have to commit an act of vandalism against the cathedral of classical physics in order to save the appearances, to make the equations match the gentle, finite glow that any blacksmith could see with his own eyes. To feel the trap more sharply, it helps to notice that the ultraviolet catastrophe was not a vague philosophical worry. It was a concrete, quantitative disaster that you could write down in numbers. If you took the honest classical formula and asked it how much total energy a warm cavity should contain, the answer it returned was not a large number. It was not even an enormous number. It was infinity. Full stop. An answer with no meaning at all in the physical world. An infinity is not the kind of error you can fix by tightening a measurement or adjusting a constant. It is a signal that something in the reasoning is broken at the root, that you have asked nature a question, and nature has handed back nonsense because one of your assumptions was never true to begin with. What made it so disorienting was the contrast between the violence of the prediction and the gentleness of the reality. The theory screamed infinity. The world answered with a soft red glow you could warm your hands beside. There is almost something comic in the mismatch, a physics so confident and so complete that it predicts the instant incineration of anyone standing near a candle, set against the plain fact that candles have lit dinners for centuries without harming a soul. The universe was being patient and finite and kind, and the most advanced theory humanity possessed was insisting, with perfect mathematical sincerity, that this was impossible. When your best description of reality is that emphatically at odds with reality itself, you're not looking at a problem to be patched. You're looking at the end of an era, whether or not anyone is ready to admit it. And the cruel joke of history is that the man who would do it was the man who least wanted to. The vandal would be the cathedral's most loyal guardian. Planck looked at the ultraviolet catastrophe not as an exciting opportunity to overthrow the old order, but as a wound in something he loved, a problem he was desperate to heal in a way that left the foundations intact. His entire goal, going in, was to find a solution that preserved classical physics, that fixed the catastrophe without breaking anything sacred. He wanted to be the man who patched the crack so well that no one would ever know it had been there. He worked on it for years, circling it, attacking it from the side of his beloved thermodynamics and the second law, trying to derive the correct radiation curve from principles he trusted. He made real progress on pieces of it. He found ways to relate the radiation to the entropy of his oscillators, bringing his cherished second law into the problem. But the full curve, the complete shape that matched the experiments across every wavelength, kept slipping away from him. The honest classical physics kept marching toward the cliff, and as the year 1900 unfolded, the experimentalists kept handing him better and better data, more precise measurements of the real curve, almost taunting him with how clean the answer was and how stubbornly the theory refused to produce it. By the autumn of 1900, Planck was cornered. The experiments were now so accurate that any correct theory had to thread an extremely narrow needle, matching the data at both the long wavelength end and the short wavelength end at the same time. There existed an old formula, Wien's law, that worked beautifully at high frequencies but failed at low ones. There would soon be another approach, later completed by Rayleigh and Jeans, that worked at low frequencies but ran straight into the catastrophe at high ones. Each captured half of reality and lied about the other half. What nobody had was the whole curve, the single expression that told the truth everywhere. And this is the moment the story tightens to a point. Planck, the careful conservative, the man who wanted above all to preserve the old order, was about to do something out of character and almost reckless. Pressed by the data, running out of principled options, he was going to guess. He was going to reach for a formula not by deriving it cleanly from the laws he trusted, but by fitting it to the answer, by working backward from the curve nature had already drawn. He was about to find the right equation before he had any idea why it was right, and the price of understanding why, when he finally paid it, would be everything he believed about the smoothness and certainty of the world. Part 4. The Formula That Arrived Too Early. In early October of 1900, on a single evening, the shape of the modern world changed, and almost no one noticed, least of all the man responsible. There was no laboratory explosion, no flash of insight on a mountaintop, no dramatic confrontation with the establishment. There was a quiet professor at his desk, juggling 2 flawed equations and a fresh batch of experimental numbers, looking for a way to splice the broken pieces together. What he produced that night was, at first, less a theory than a clever repair. But that repair would turn out to be exactly, perfectly correct, and the strangeness of having the right answer without knowing why is the engine that drives everything that follows. Here is the situation Planck found himself in. On one side sat Wien's law, the formula that matched the experiments beautifully at the short wavelength high-frequency end of the spectrum, the very region where the catastrophe lurked. Wien's law tamed the ultraviolet, but it failed in the infrared, predicting too little energy at long wavelengths where the real curve stayed stubbornly higher. On the other side sat the honest classical result, the one that respected equipartition and matched the data at long wavelengths, but then ran screaming toward infinity at short ones. Planck had, in effect, 2 partial truths, each correct exactly where the other was wrong. One described the blue end faithfully and lied about the red. The other described the red end faithfully and lied about the blue. What happened next is one of the most human moments in the history of science, because Planck did not solve this by some grand act of derivation. He interpolated. He looked at the mathematical expression for the entropy of his oscillators in the regime where Wien's law worked, and he looked at the expression that would be needed in the regime where the classical result worked, and he asked himself whether there was a simple way to write something that smoothly bridged the two. He found one. By making what he later admitted was essentially a fortunate guess, a mathematically natural interpolation between the 2 limiting behaviours, he wrote down a single formula for the radiation curve, and then he compared it to the experimental data across the whole spectrum, every wavelength, every temperature. It fit. Not approximately, not in some regions. It fit everywhere, across the entire measured range, with a precision that matched the best experiments anyone could perform. On the 19th of October 1900, Planck presented this formula to the German Physical Society almost as a footnote, a small improvement on Wien's law. That very night, the experimentalist Heinrich Rubens went home and checked Planck's formula against his own latest, most careful measurements, the ones reaching far into the infrared where the other theories failed. The next morning Rubens came to Planck and told him the agreement was complete. Wherever the data could be measured, Planck's formula tracked it exactly. The curve that had defeated the finest physics in Europe had been captured at last, written in a single line. It is worth lingering on what kind of victory this actually was, because it was unlike the triumphs Planck had imagined for himself. He had always wanted to arrive at truth from above, by reasoning down from secure principles to their necessary consequences, the way a geometer proves a theorem. What he had done instead was closer to detective work, or even to guessing. He had looked at the answer nature had already written, and worked backward toward a formula that could produce it, guided as much by mathematical taste and a feel for the shape of the problem as by any chain of deduction. For most scientists, a result that fit the data this perfectly would have been cause for unreserved celebration. For Planck, It was shadowed by unease, because he knew he had reached the right house without yet knowing the road that led there. This is one of the most honest things about him, and one of the most instructive things about how science actually moves. We're often taught that discovery proceeds in a clean line, hypothesis to prediction to confirmation, reason marching steadily forward. The real story is messier and more human. Sometimes the answer arrives first, as a lucky pattern or a fortunate guess, and the understanding of why it is true comes limping along behind, sometimes years later. Planck had the equation in October. He would spend the following weeks in the hardest intellectual labour of his life trying to earn it, trying to find the principle that would make his lucky formula not just correct but inevitable. And the principle he would finally uncover would be so unwelcome that finding it felt less like solving the riddle and more like reading a sentence he wished had never been written. You might think this would be the happy ending, the moment of triumph, and in one sense it was. Planck's radiation law is correct. It is still in every physics textbook today, more than a century later, unchanged. It describes the light from this glowing oven, from the filament in a lamp, from the surface of the sun, from the faint warmth left over from the birth of the universe itself. It is one of the most successful equations ever written. But for Planck, the man who had found it, that October formula was not an ending. It was the beginning of a torment, because he had done something that every honest scientist knows is only half the job. He had found a formula that worked without understanding why it worked. He had the answer to the riddle, but not the reasoning. And Planck was not the kind of man who could live with that gap. He described what came next as the most strenuous work of his entire life. For several weeks, in the late autumn of 1900, he threw himself at the problem of deriving his lucky formula from first principles, of finding the physical reason that nature should glow in exactly this way and no other. He had the target. He knew precisely what equation he had to arrive at. The question was what assumption, what piece of underlying physics, would force the universe to produce that particular curve. He was reverse engineering reality, working backward from a known answer to the hidden law that demanded it. And the law he was about to uncover would be one he found almost impossible to accept. To get there, Planck finally did the thing he had resisted his whole career. He turned to Ludwig Boltzmann's statistical method, the very approach he had spent years arguing against. Remember, Planck had defended the idea that the second law of thermodynamics was absolute, beyond mere probability. Boltzmann had insisted it was statistical, a matter of counting the overwhelming number of disordered arrangements against the rare ordered ones. Now, cornered, desperate to derive his formula, Planck swallowed his objection and picked up Boltzmann's tool. He decided to calculate the entropy of his oscillators by counting the number of ways energy could be distributed among them, exactly the kind of probabilistic bookkeeping he had once found almost distasteful. This was already a small surrender, a man reaching for a method he had publicly disliked because nothing else would work. But the statistical method came with a strange technical requirement, and this is the hinge of the entire story, the place where physics quietly breaks. To count the number of ways to distribute energy among his oscillators, Planck had to treat the energy as if it came in finite chunks. Counting requires countable things. You cannot count a smooth, continuous flow. So as a mathematical device, he divided the total energy into small, equal packets, little indivisible units, so that he could tally up the different ways of handing them out to the oscillators. He fully expected that this was a temporary trick, a scaffolding to be removed once the building stood. The plan, the obvious classical plan, was to make these energy packets smaller and smaller, shrinking them towards zero, until the artificial graininess melted back into the smooth continuity that all of classical physics demanded. At the end of the calculation, the size of the packet was supposed to vanish, leaving a clean, continuous result behind. And here is where the universe refused. When Planck carried out the calculation and shrank the energy packets towards zero, hoping to recover his formula, he did not get his formula. He got the catastrophe back. He got the wrong answer, the infinite blaze of the ultraviolet. The only way, the single solitary way to make the mathematics produce his correct, experimentally perfect radiation curve was to refuse to let the packets vanish. He had to keep them at a definite finite size, and not just any size. The size of each energy packet had to be tied directly to the frequency of the oscillator, so that high-frequency oscillators could only accept energy in large lumps, while low-frequency ones could accept it in small lumps. The energy of a single packet had to equal the frequency multiplied by a new constant of nature, a tiny number that Planck now had to introduce into physics for the first time. That number is the one we now call Planck's constant. To appreciate the strangeness of introducing a brand new constant of nature, you have to understand how rare and how serious such a thing is. The fundamental constants are the handful of numbers that set the basic character of reality, the fixed dials of the universe. The speed of light is one. The constant of gravitation is another. These are not quantities you adjust or derive from something deeper. They are the bedrock values that everything else is built on, and for a physicist to add a new one to the list is an enormous claim, almost an act of cosmic presumption. It is to say that the universe has a feature so basic that it deserves its own permanent number, woven into the structure of all things. Planck did not want to make that claim. He wanted his constant to be temporary, a quantity that would shrink to zero and vanish once a better, more classical derivation came along. But the number refused to behave like a temporary thing. It had a definite, stubborn, non-zero value, and that value showed up not as an adjustable fudge factor, but as something the data demanded with precision. The universe was insisting through the glow of the cavity that this new constant was real and fixed and fundamental, as permanent as the speed of light itself. Planck had reached for a passing convenience and found, in his hand, one of the master numbers of reality, a dial that had been set since the beginning of time, and that he was the first human being ever to read. Its value is fantastically small, about 6.626 divided by 10 followed by 33 more zeros, in the standard units physicists use, a quantity so minuscule that it had never needed to appear in any equation before. To get a sense of how small that is, the energy in a single packet of visible light is roughly a billionth of the energy your body uses in a single heartbeat. This is why the graininess had stayed hidden for so long. The steps are so unimaginably tiny that, at the scale of fires and ovens and human bodies, energy looks perfectly smooth, the way a beach looks like a continuous surface until you kneel down and see that it is made of separate grains of sand. But the smallness of the number did not soften the blow. The point was not how big the packets were. The point was that they could not be allowed to disappear. For the formula to match reality, energy had to come in discrete units. Nature, at its foundation, was not a smooth flow. It was lumpy. It counted. And Planck, the man who had devoted his life to the seamless, continuous, deterministic clockwork of classical physics, the man who wanted nothing more than to defend the old order, now held in his hands the proof that the old order was wrong at its very root. He had found his derivation. He had also found the thing he would spend the next decade of his life trying, with everything he had, to make untrue. He had the answer. Now he had to decide whether he could bear to believe it. Part 5. The night. He paid the price. Some discoveries feel like winning. This one felt like losing something that could never be recovered, and the man at the centre of it knew it even as he wrote the words down. Planck had his derivation. He had the physical assumption that produced his perfect formula. But that assumption demanded that he give up not one but several of the things he held most sacred about the universe, and he understood the size of that sacrifice with a clarity that almost no one around him shared. To make the equation work, he had to accept that energy comes in discrete packets. To count those packets, he had to embrace Boltzmann's statistical view of entropy, the very idea he had fought, and in doing so, he had to let go of his belief that the second law of thermodynamics was an absolute, exceptionless truth, and accept that it too was merely a matter of overwhelming probability. He was not surrendering one conviction. He was surrendering a whole world view. He would say later, in a letter written decades afterward to the American physicist Robert Williams Wood, that what he had done was an act of desperation. Those are his own words, and they are worth holding carefully, because they come from the man himself, looking back across 30 years at the night he changed the world. He wrote that he had been by nature peaceful and disinclined to questionable adventures, but that by then he had been struggling with the problem of the equilibrium between matter and radiation for 6 years without success, and he knew the problem was of fundamental importance. He had found the formula that expressed the truth, and so, he explained, a theoretical interpretation had to be found at any cost, no matter how high. It was, he said plainly, an act of desperation. He was ready to sacrifice any of his previous convictions about physics. Sit with that phrase, an act of desperation. This is not how we usually imagine the birth of the most important idea in modern science. We imagine confidence, vision, a thinker striding boldly into the future. Instead, we have a careful, conservative man, cornered by his own honesty, forced against every instinct he possessed to introduce something he did not believe in, because the alternative was to deny the data in front of him. He did not leap into the quantum, he was pushed, and he went in with his eyes half closed, hoping the whole time that it was temporary. There is a phrase scientists sometimes use for this kind of result. They call it being forced by the data, and it is one of the most powerful experiences a thinker can have, though it is rarely a happy one. To be forced by the data means that your own preferences no longer matter, that you have followed honest reasoning to a conclusion you would never have chosen, and that the only way to escape it would be to lie. It is the moment the universe stops being a thing you study, and becomes a thing that overrules you, that tells you how it is whether or not you approve. Every great scientist eventually meets this moment, the point where reality refuses to bend to what they hoped, and the measure of the scientist is what they do when they get there. Planck met that moment in the autumn of 1900, and what he did ultimately was submit. He did not like the answer. He spent years trying to find a way around it. But he did not deny it, did not hide it, did not pretend the data said something gentler than it did. He let himself be forced, and he wrote down the conclusion the universe had pressed into his hands, even as part of him recoiled from it. That submission, reluctant and pained as it was, is the reason we remember him. The universe forces many people, and some of them flinch away and refuse to look. Planck looked. He paid the price the data demanded, in the currency of his own most cherished beliefs, and the receipt for that payment is the equation that opened the modern age. On the 14th of December, 1900, Planck stood before the German Physical Society in Berlin and presented the derivation. That date is now carved into the history of science as the birthday of the quantum, the moment the modern era of physics began. And I want you to actually be in that room, because the gap between what was happening and what it looked like is the most haunting thing about it. You're sitting in a lecture hall in Berlin on a cold December evening. The gas lamps are lit. There is the usual quiet shuffle of an academic audience, men in dark coats with notebooks open on their knees. At the front, a slight, balding, formal man with a careful moustache stands and begins to speak in a measured, unhurried voice. He is not theatrical. He does not raise his voice or pause for effect. He works through the mathematics of heat and radiation the way he would work through any technical problem, step by careful step. He explains that to derive the radiation law, one must assume the energy of the oscillators is restricted to whole multiples of a small unit, a quantum, equal to a new constant times the frequency. He says it plainly, almost apologetically, a strange necessity of the calculation. Around the room, pens move. A few colleagues nod. No one gasps. No one stands. No one in that hall, perhaps not even the man speaking, fully understands that the floor of physics has just silently given way beneath them, that the smooth and certain universe they all believe in has, in this quiet moment, in this flat technical voice, just ended. The lamps hiss, the lecture concludes. People gather their coats and step out into the December night, talking of other things. What I find almost unbearable about that scene is how perfectly it captures the way the largest changes in history actually arrive. We expect revolutions to feel like revolutions, to come with sirens and trumpets, with everyone in the room aware that the ground has shifted. But the truth is that the moments that reshape everything usually look, from the inside, like ordinary moments. A man reads a paper to a half-attentive audience. A clerk files a document. A small decision is made in a quiet room. The significance only assembles itself later, in hindsight, when we look back and realise that the river of history bent at a point no one noticed while they were standing in it. The 14th of December, 1900, was such a point, and almost no one present felt it bend. And there is a particular loneliness in being the one person in the room who senses the size of the thing. Planck could not be certain, that evening, of everything his quantum would come to mean, but he understood, more than anyone listening, that he had been forced to do something drastic, that he had paid a price in principles to buy that perfect formula. He carried that knowledge out into the cold alone, while his colleagues discussed dinner and the weather and the small business of academic life. The most important idea of the coming century had just been spoken aloud for the first time, and the man who spoke it went home not in triumph but in a kind of troubled quiet, already wondering whether there might be some way, any way, to take a part of it back. The revolution had a father, and its father was already, that first night, half hoping it had not been born. That is how the revolution arrived. Not with thunder, but with a footnote delivered in a tired voice by a man who wished it were not true. And the deepest evidence that the world did not understand what had happened is that the world, including Planck himself, treated it as a minor technical result for years afterward. The quantum was born unrecognized, wrapped in the language of a routine derivation, carried out of that hall in the notebooks of men who thought they had attended an ordinary meeting. Planck went home to a changed universe that looked exactly like the old one. His children were asleep, his house was the same, and yet he carried in his mind a number, a tiny constant, that he already sensed might be one of the most important quantities in all of nature, ranking alongside the speed of light and the constant of gravitation. There is a story, told by his son Erwin, that around this time Planck took him for a walk and said that he had made a discovery as important as those of Newton. If the story is true, it tells you that some part of Planck knew exactly how large this was, and yet the very same man would spend the next 10 years trying to prove that the most important part of his own discovery was an illusion. Both things were true at once. He sensed its size, and he could not bear its meaning, and those two feelings would tear at him for the rest of his career. Because what he had introduced was not just a new constant or a new formula, it was a crack in the oldest assumption of all, the assumption that nature does not jump. Since the time of the ancient Greeks, thinkers had repeated a phrase that captured the deepest intuition of classical physics. Nature, they said, does not make leaps. Everything flows. Every change can be divided into smaller changes. Between any two states there is always an intermediate one. Motion is smooth, energy is smooth, time is smooth, the world is a continuous river with no smallest drop. Planck's quantum said no. It said there is a smallest drop. It said energy comes in steps, that there are gaps in the river, places where nature does leap, jumping from one allowed value to the next with nothing in between. The continuous world was a comfortable illusion stitched together by the smallness of his constant. Underneath, reality was granular, discrete, counted. And Planck, standing at the edge of this discovery, did the most understandable and most poignant thing a person can do when they find a truth they cannot stand. He decided it could not really be true. He decided that the quantum must be a mathematical trick after all, a piece of temporary scaffolding, a bookkeeping device that a deeper, more classical understanding would eventually dissolve. He resolved to find that deeper understanding, to derive his formula some other way, a way that let the continuity of the universe survive. He set out, in other words, to disprove the most important thing he would ever discover. And the story of the next decade of his life is the story of a brilliant man trying and failing over and over again to bury his own revolution before it could escape. Part 6. The Revolution That Nobody Noticed. For about 5 years after that December lecture, the most important discovery in the history of physics simply sat there, ignored, like a letter delivered to the wrong house and left unopened on a shelf. This is one of the most astonishing facts in the whole story, and it is worth dwelling on, because we are taught to imagine that great truths announce themselves, that the world recognizes genius when it appears. The reality is almost the opposite. The quantum was born, and then for half a decade, almost nobody, including its own author, was willing to take it seriously as a statement about how the universe actually works. Part of the reason is that Planck himself presented it so cautiously. He did not go around proclaiming that energy was fundamentally discrete and that classical physics had fallen. He framed his energy packets as a formal step inside a derivation, a way of counting that produced the right answer. Whether nature was really, physically granular, or whether this was just a mathematical convenience, he left carefully open, and in his own mind he leaned strongly toward the second view. He wanted it to be a convenience. He wanted some future, cleverer derivation to come along and reproduce his formula without requiring real, physical lumps of energy. So the man best positioned to champion the quantum spent these years quietly hoping it would turn out to be less than it was. And his colleagues, the broader community of physicists, mostly did not engage with it at all. Planck's radiation formula was accepted and used because it worked, because it matched the experiments and let engineers and scientists calculate what they needed. But the strange assumption underneath it, the quantization of energy, was treated as Planck's peculiar private route to a useful result, not as a discovery about reality. People used the formula and ignored the foundation. It was as if everyone agreed the destination was correct while politely declining to look at the disturbing road that led there. The catastrophe had been solved, the light bulbs could be designed, and the unsettling philosophical price could be left in a drawer. To understand how easy it was to look away, you have to remember again just how small Planck's constant is, because the smallness is not a minor detail. It is the camouflage that let the quantum hide in plain sight for so long. The constant is a number with more than 30 zeros after the decimal point before you reach the first significant figure. In the world of everyday objects, of moving balls and flowing water and warming rooms, the energy steps that the quantum demands are so unimaginably tiny that no measurement of ordinary things could ever reveal them. A swinging pendulum does, in truth, only occupy discrete energy levels, but the levels are spaced so finely, so close together, that the swing looks perfectly smooth, the way a film looks like continuous motion even though it is made of separate frames. Classical physics is not exactly wrong about the everyday world. It is an extraordinarily good approximation, a description that becomes essentially perfect whenever the quantum steps are too small to matter, and for almost everything humans had ever measured, they were far too small to matter. This is why Planck could half believe his own constant was a fiction. In every familiar situation, you could let the quantum shrink towards zero in your imagination and recover the smooth classical world, and nothing would seem to go wrong. The only place the graininess refused to disappear was inside that glowing cavity, in the radiation problem itself, where the high frequencies forced the issue. It was a single, narrow doorway through which the strangeness leaked. There is a deeper irony in this period that is easy to miss, and it concerns the nature of scientific courage. We usually think of courage in science as the willingness to propose a bold new idea. But Planck's situation reveals a second, stranger kind of courage. The courage required to take your own ideas seriously when doing so frightens you. Planck had the boldness to introduce the quantum. What he lacked, in these years, was the harder boldness to believe it, to look at his own creation and say, out loud, This is not a trick. This is how the world is made. That second step, the step from having an idea to trusting it, can be far more difficult than the first, especially when the idea overturns everything you hold dear. It is one thing to write a revolutionary sentence. It is another to stake your understanding of reality on it. This gap between proposing and believing runs all through the history of the quantum, and Planck is only its first example. Again and again, the people who built quantum physics found themselves unable to fully accept the world their own equations described. They produced the mathematics, confirmed it against experiment, used it to make the most accurate predictions in the history of science, and then recoiled from what it seemed to be saying about reality. The quantum has always been easier to use than to believe. Planck began that tradition in these quiet years after 1900, holding a discovery at arm's length, using its formula while refusing its meaning, and in doing so he became the first member of a long line of brilliant people who would spend their lives doing physics they could not bring themselves to trust. And it would have been so easy, so comfortable, to assume that the doorway was a mistake in the wallpaper, rather than an opening into another room. Planck spent these years trying to paper it over, returning again and again to the radiation problem, searching for a derivation that would let him keep the formula and discard the lump. There is something quietly moving about this period of his life, because it shows you a great scientist at war with his own result. Planck was not a foolish man clinging to error. He was one of the most rigorous thinkers of his generation, and his discomfort was not stubbornness for its own sake. He understood, perhaps better than anyone, exactly what was at stake if the quantum were real. He saw that if energy truly came in discrete packets, then the entire edifice of classical physics, the continuous, deterministic, infinitely divisible world that had been built up over 2 centuries, would have to be rebuilt from the ground up. He was not refusing a small revision. He was staring at the demolition of everything he had been trained to revere, and he was hoping, with a kind of scientific prayer, that it would not be necessary. Meanwhile, the constant itself was beginning to whisper that it was something more than a trick, for those willing to listen. Planck noticed something remarkable about his new number. By combining it with 2 other fundamental constants of nature, the speed of light and the constant of gravitation, he found he could construct natural units of length, time, and mass. Units built entirely out of the deepest constants of the universe, owing nothing to human conventions like meters or seconds, which were originally tied to the size of the Earth and the swing of a pendulum. These natural units, now called the Planck length, the Planck time, and the Planck mass, are absurdly extreme. The Planck length is about 100 billion times smaller than the nucleus of an atom. The Planck time is the duration it takes light to cross that almost inconceivably tiny distance. Planck himself sensed that these units, born from his constant, would mean the same thing to any intelligence anywhere in the cosmos, that they were in some sense woven into the structure of reality itself. A man does not usually build the fundamental yardsticks of the universe out of a meaningless mathematical fiction. Some part of him surely knew. The natural units Planck built from his constant deserve a moment of wonder, because they reveal just how far the number reaches. Think about how we usually measure things. A meter was originally tied to the size of the Earth. A second was tied to the turning of our planet. An hour, a foot, a pound. Nearly every unit we use grew out of some accident of human history or some feature of our particular world. They are local, parochial, ours. But the units Planck constructed owe nothing to Earth or to humanity. They are built purely from the constants that govern light, gravity, and the quantum, the same everywhere in the universe, and so they would mean exactly the same thing to a civilization on the far side of the galaxy as they mean to us. They are in a sense the units the universe would choose for itself, and the scales they point to are almost beyond imagining. The Planck length is so small that compared to it, a single atom is larger than the entire solar system is compared to a grain of sand. It marks the level at which our current understanding of space and time is thought to break down entirely, where the smooth fabric of reality may itself dissolve into something granular and quantum. Planck, working in the first years of the 20th century, had no way to know how prophetic these units would prove to be. But he sensed their significance, sensed that his little constant had handed him a ruler measured against the deepest structure of existence. A man does not stumble onto the natural yardsticks of the cosmos by accident. Whatever his doubts, some part of him understood that he had touched something close to the bottom of the world, and yet he held back. He used the formula, he explored the constant, and he refused the final step of declaring that the universe was truly, physically quantized. He stood at the threshold of his own discovery and would not walk through. For 5 years the quantum waited, fully born but unacknowledged, its true significance hidden behind the modesty of its author and the indifference of his colleagues, protected by the smallness of a number with 30 zeros. It would take someone else, someone younger, bolder, and far less invested in preserving the old order, to pick up Planck's reluctant idea and say the thing Planck could not bring himself to say. It would take a 26-year-old patent clerk in Switzerland working in his spare time to look at Planck's energy packets and declare that they were not a mathematical convenience at all. They were real. Light itself was made of them. And with that single, fearless claim, the quantum that Planck had tried to keep contained inside a derivation would break loose into the world, and the long, painful second act of Planck's life, the years of trying to make it disappear, would truly begin. Part 7. The years he spent. Trying to take it back. Imagine making the greatest discovery of your life, and then spending the next 10 years trying to prove yourself wrong. Not refining it, not extending it, trying to undo it, to reach back into the work and pull out the very thing that made it revolutionary, so that the comfortable old world could close over the wound and heal as if nothing had happened. That is what Max Planck did, and it is one of the strangest and most human spectacles in the history of thought. The father of the quantum became its most determined opponent, and the opponent he was fighting was himself. His goal in these years was specific and revealing. He wanted to keep his radiation formula, which he knew was correct, while getting rid of the physical reality of the energy quantum, which he could not accept. He was trying to find a way to derive the right answer without the lump, to show that the discreteness was an artifact of his method rather than a feature of nature. Over and over, he constructed new versions of his theory, new derivations, new physical pictures, each designed to let continuity survive. He would allow the quantum in by the smallest possible door, restrict it to the narrowest possible role, and try to push everything else back into the smooth classical framework he loved. He tried to make it disappear. That phrase deserves to be held up and looked at directly, because it is the secret shape of this entire chapter of his life. He tried to make it disappear. He had found a gap in the river of nature, a place where energy jumps rather than flows, and his every instinct was to fill that gap back in, to smooth the water over and pretend the river had always been continuous. One of his most revealing attempts came around 1911 and 1912 in what is sometimes called his second theory. In this version, Planck proposed a compromise designed to soften the strangeness. He suggested that oscillators might absorb energy continuously, in the smooth classical way, and only emit energy in discrete quantum jumps. It was a halfway house, a careful diplomatic treaty between the old physics and the new, an attempt to let nature be continuous on the way in, and only grudgingly granular on the way out. He was bargaining with his own discovery, trying to give the quantum as little territory as he possibly could. If you have ever found yourself negotiating with a truth you did not want, you already understand the inner shape of these years, even if you have never thought about physics in your life. We all know what it is to suspect something, and to spend our energy constructing reasons why it might not be so. We know the particular exhaustion of arguing against a conclusion that some quiet part of us has already accepted. Planck's decade of retreat is that universal human experience carried out at the highest level of intellect and written across the foundations of science. He was, in the most literal sense, a man who could not make peace with what he knew, and who kept returning to the same painful place, hoping that this time the answer would be different. What gives the story its dignity is that he never once cheated. A lesser man, faced with a truth he hated, might have fudged the mathematics, looked away from the inconvenient result, quietly buried the data that did not fit. Planck did none of that. Every escape route he built he tested honestly, and every time it failed he admitted the failure. His resistance lived entirely in his hopes, never in his rigour. He wanted the quantum to be unreal, but he refused to lie to himself about whether it was, and so his very honesty kept marching him back, again and again, to the conclusion he was trying to flee. There is something almost noble in that. A man fighting his own discovery with one hand while refusing with the other, to let himself win by any means he did not believe were true. He lost the fight precisely because he was too good a scientist to win it dishonestly. This second theory had a curious side effect that tells you how far he was digging. It led him to the idea that oscillators retain a residual energy even at the coldest possible temperature, at absolute zero, a leftover trembling that never fully stops. This notion, of a lowest energy that can never be removed, was an early sign of what would later be called zero-point energy, a genuinely profound concept that quantum mechanics would eventually confirm in a deeper form. So even in the act of trying to tame the quantum, Planck kept stumbling onto more quantum strangeness. The harder he pushed against the door, the more it opened. Every attempt to contain the revolution uncovered another piece of it. It was as if the universe kept handing him further proof of the very thing he was trying to deny. And none of his retreats worked. None of his alternative derivations succeeded in banishing the quantum while keeping the formula. Every honest path led back to the same unavoidable conclusion. Energy is discrete. The constant does not vanish. Nature at its root counts. Planck was too good a physicist to fool himself along with any particular escape route, and so each attempt would eventually collapse, and he would be left again facing the thing he could not stand. There is a quiet heroism in this, and also a quiet tragedy. He was rigorous enough to keep testing his escapes, and honest enough to admit when they failed, which meant he was condemned to discover again and again that his own revolution was real. You have to understand that for Planck this was not an abstract intellectual puzzle. It was closer to grief. The continuous deterministic universe was not just a theory to him. It was an article of faith, almost a moral order. He believed that the world was lawful, that every effect followed from its cause in an unbroken chain, that a sufficiently complete knowledge of the present would allow you, in principle, to read off the entire future. This was the picture of reality that had given his life its shape and meaning. And his own discovery was the first crack in that picture, the first hint that the chain of causes might have gaps in it, that the future might not be fully written, that chance and discreteness might live in the basement of reality. To accept the quantum fully was to mourn the universe he had loved. So he resisted, not out of vanity, but out of a kind of loyalty to a vanishing world. There is something almost unbearably tender about a man working late into the night, year after year, trying to disprove the most important thing he will ever do, because the alternative is to admit that the cosmos is stranger and less certain than he can bear. Picture him at his desk in Berlin, the same careful handwriting, the same rigorous patience he brought to everything, now turned against his own creation. He is not trying to win fame. Fame would come from embracing the quantum, from planting his flag on the new continent he had discovered. He's trying to do the opposite. He's trying to sail back and pretend the continent is not there, to redraw the map of reality so that the frightening new land disappears beneath the familiar sea, and the sea will not stay drawn. The land keeps rising. There is a thought that must have haunted him in these years, and it is the thought that gives this whole chapter its undertow of dread. If the quantum were real, then Planck had not merely added a new fact to physics. He had removed something permanently from the human understanding of the world, and he could feel its absence even before he could name it. The thing he had removed was the promise that the universe was, at bottom, the kind of place a human mind could fully grasp. The old physics had carried that promise quietly inside it, the assurance that with enough patience and enough genius, everything could one day be known, every cause traced, every motion predicted. Planck's constant was the first crack in that promise, the first sign that some part of reality might be closed to us forever, not by accident, but by design. A man who loved certainty the way Planck did would feel that absence as a kind of bereavement, a loss with no body to bury. He could not point to exactly what was gone, because what was gone was a feeling about the world, a confidence so complete it had never needed to be stated. And now, because of his own work, that confidence was leaking away, and he could not stop it, and he could not get it back. This is why his resistance went on so long and cut so far. He was not defending a formula or a preference. He was defending the knowability of existence itself, the right of the human mind to one day understand everything, and he was losing that defence to the evidence his own hands had gathered. No wonder he kept fighting. He was trying to hold the door not against a single strange idea, but against the permanent humbling of everything he believed thinking could achieve. This is the emotional centre of the whole story, the still point around which everything else turns. A man who found a truth so large and so disturbing that he spent a decade of his finite life trying to talk the universe out of it. We tend to celebrate scientists for their courage, their willingness to follow the evidence wherever it leads. Planck's story is more complicated and, in a way, more honest about what it costs to be human in the face of an overwhelming truth. He did follow the evidence eventually, but first he fought it, because it asked him to give up too much, and he was not made of stone. He was a man who loved a particular vision of the world, and that vision was dying in his hands, and he was not ready to let it go. But while Planck was quietly trying to bury his discovery in Berlin, the idea had already escaped. It had reached a young, unknown thinker in Switzerland who felt none of Planck's loyalty to the old order, who had nothing invested in keeping the universe smooth, and who was perfectly willing to say out loud the thing Planck most dreaded hearing. And what that young man did with Planck's reluctant little constant would make it impossible, forever, to put the quantum back in its box. The genie was already out. Planck just did not know it yet. Part 8. The Man Who Made It Worse. In the year 1905, a young man working as a clerk in the Swiss Patent Office in Bern published a handful of papers in his spare time that would each, on its own, have been enough to make a career. One of them explained the random dance of pollen grains in water and gave us proof that atoms are real. One of them was the special theory of relativity, which rewove space and time. One of them, the one that mattered for the photoelectric effect, would eventually win him the Nobel Prize. That young man was Albert Einstein, and the paper that concerns us here is the one he himself called revolutionary, the only one of his own works he ever described that way. It took Planck's reluctant little energy packet and did the one thing Planck had spent 5 years refusing to do. It said the packet was real. Here is the difference between the two men, and it is the whole story in miniature. Planck had introduced energy quanta as a property of his oscillators, the vibrating charges in the walls of the cavity. He had been careful to confine the strangeness to the way matter emits and absorbs radiation, leaving open the hope that light itself was still the smooth, continuous wave that classical physics described. Einstein refused that comfort. He proposed that light itself, radiation travelling through empty space, is made of discrete packets of energy, individual grains of light, each carrying an energy equal to its frequency times Planck's constant. Light was not a continuous wave that merely happened to be emitted in lumps. Light was the lumps. The quantum was not a quirk of how furnaces glow. It was woven into the nature of light, and therefore into the nature of everything light touches. Einstein did not pull this out of thin air. He used it to explain a real and stubborn puzzle called the photoelectric effect. When you shine light on certain metals, the light can knock electrons out of the surface. Classical physics, treating light as a continuous wave, made very clear predictions about how this should behave, and the predictions were wrong in a specific and revealing way. The wave picture said that brighter light, carrying more energy, should knock electrons out with more force, and that the colour of the light should not much matter. The experiment said the opposite. The energy of the ejected electrons did not depend on how bright the light was at all. It depended only on the colour, the frequency. Dim blue light could kick electrons out hard, while intensely bright red light, below a certain frequency, could not kick them out at all, no matter how bright you made it. Einstein's grainy light explained this perfectly. If light comes in packets whose energy depends on frequency, then a single high-frequency packet, a blue or ultraviolet grain, carries enough energy to knock an electron free, while a low-frequency packet, a red grain, simply does not, no matter how many of them you throw at the metal. Brightness only means more packets, more grains, but if each grain is too weak, piling up more of them changes nothing. It was an elegant, decisive, and deeply unsettling explanation, and it made Planck's quantum into something far more dangerous than a footnote about furnaces. It made it a statement about the fundamental constitution of light. The contrast between Planck and Einstein in these years is one of the most illuminating pairings in the history of science, because it shows you that temperament can matter as much as talent. Both men were brilliant. Both understood the mathematics completely. But where Planck was anchored to the past, loyal to the continuous world he had grown up inside, Einstein was unencumbered, a young outsider with no investment in protecting the old order and no fear of where the logic led. Einstein looked at the same energy packet Planck had introduced and felt none of the dread. He felt only the pull of the question, the simple willingness to ask what would be true if the packet were real, and to follow that question without flinching wherever it went. The same idea that Planck held at arm's length, Einstein embraced with both hands. It would be a mistake, though, to make Planck the villain and Einstein the hero of this moment, because the relationship between them was far warmer and more generous than that. Planck genuinely admired the younger man and did more than almost anyone to advance his career, recognizing his greatness while disagreeing with his boldest claim. There is something deeply human in this picture. Two men of different generations and different temperaments, one reaching forward and one holding back, bound together by mutual respect even as they pulled in opposite directions on the single most important question in physics. Planck could not follow Einstein into the grainy light, and he said so plainly. But he never stopped honouring the mind that had gone where he could not. The father of the quantum and its first true believer walked beside each other for years, agreeing on almost everything except the one thing that mattered most. It is tempting looking back to wish that Planck had simply trusted his own discovery from the start, that he had skipped the decade of doubt and planted his flag boldly on the new world he had found. But the wish misunderstands what made the discovery so monumental in the first place. The quantum was not a small adjustment that a reasonable person could accept over a weekend. It was an assault on the most basic intuition human beings have ever held about how the world works, and the fact that even its own author could not easily swallow it is the surest measure of how revolutionary it truly was. Easy ideas are accepted easily. The ideas that change everything are the ones that even their discoverers have to be dragged toward. Protesting, because those ideas ask us to give up something we did not know we were holding. Planck's long reluctance is not a footnote to his greatness, it is the proof of it, the visible struggle of a first-rate mind being forced to surrender a world-view that had felt as certain as the ground underfoot. Every year he resisted is a year that testifies to the size of what he had found, and his eventual sorrowful acceptance is all the more moving because it was so hard won. And how did Planck respond to the young man who had taken his idea and made it real? With a mixture of admiration and profound discomfort that perfectly captures his divided soul. Planck recognized Einstein's genius early and championed him generously. He was one of the first established physicists to take relativity seriously, and he worked to bring Einstein into the higher circles of German science. But on the question of a light quanta, Planck could not follow him, and he said so. When Planck and several other leading physicists nominated Einstein for membership in the prestigious Prussian Academy of Sciences in 1913, they wrote a glowing recommendation praising his contributions across the whole of physics. And then, in that very same document, they added a remarkable caveat. They wrote that the fact that Einstein might sometimes have missed the mark in his speculations, as for example in his hypothesis of light quanta, should not be held too much against him, since it was impossible to introduce genuinely new ideas, even in the most precise sciences, without occasionally taking a risk. Read that again and feel the weight of it. In the act of recommending Einstein for one of the highest honours in science, Planck and his colleagues felt compelled to apologise for the light quantum, to file it under youthful overreach, a forgivable misstep by an otherwise brilliant mind. The very idea that would later earn Einstein his Nobel Prize was being described by the man who had unknowingly fathered it as a speculation that had missed the target. Planck had introduced the quantum and then watched it grow into something he disowned. And here he was, signing his name to a document that gently called his own offspring a mistake. The universe, however, kept siding with Einstein. The grainy theory of light made precise, testable predictions about the photoelectric effect, and an American experimentalist named Robert Millikan set out to prove it wrong. Millikan disliked Einstein's light quanta as much as anyone, and he spent the better part of a decade performing meticulous experiments designed to expose the theory's failure. Instead, to his own evident frustration, his careful measurements confirmed Einstein's predictions with great precision. By around 1915, the experimental case was overwhelming, even though Millikan himself remained reluctant to embrace the physical picture that his own data supported. This became a pattern that would repeat throughout the quantum revolution. Brilliant conservative men would set out to defeat the quantum, and the quantum would defeat them, turning their own rigour into further evidence for the thing they hoped to destroy. So by the second decade of the 20th century, the situation had become impossible to contain. Planck's constant was appearing in more and more places. It governed the glow of the cavity. It governed the photoelectric effect. Soon, in 1913, a young Danish physicist named Niels Bohr would use it to explain the structure of the atom itself, showing that electrons could only occupy certain discrete orbits, jumping between them by emitting or absorbing single quanta of light. The constant Planck had introduced in desperation was turning up at the foundation of matter, the foundation of light, and the foundation of energy. It was not a local quirk. It was a master key, and it unlocked the same door everywhere. Planck, to his lasting credit, was too honest to deny what was happening forever. Slowly, reluctantly, across these years, he came to accept that the quantum was real, that his desperate device described something true about the world. He received the Nobel Prize in Physics, awarded for the discovery of energy quanta, recognition that the thing he had tried to bury was in fact one of the greatest discoveries ever made. But acceptance is not the same as peace. He had surrendered to the quantum the way a man surrenders to a grief he can no longer outrun. And the deepest part of the story, the part that makes Planck more than a historical figure, is that his reluctance turned out to be a kind of foresight. He had sensed, before almost anyone, that this discovery would not stop at light bulbs and atoms. He had sensed that it would reach all the way down and pull the floor out of reality itself, and in the years to come, the universe would prove him right in ways that even he had not imagined, ways that would have justified every sleepless night he spent trying to make it disappear. Part 9. What he had actually found. We have been telling this story as the tale of a reluctant man and a stubborn constant, and that is true. But now we have to turn and look directly at the thing itself, at what Planck had actually uncovered when he was forced to let energy come in lumps. Because the reason this story still matters, the reason it is more than a charming historical anecdote, is that the quantum did not stay small. It started as a fix for the colour of a furnace, and it ended by dissolving the deepest assumptions human beings had ever made about what is real. Planck was right to be afraid. He just could not yet see the full shape of what he was afraid of. Start with the simplest thing he found, the discreteness itself. Before the quantum, the universe was imagined as perfectly continuous. You could always, in principle, take a smaller step, a gentler nudge, a finer division. Energy could be any value at all. There was no smallest amount of anything. Planck's constant put an end to that. It said there is a smallest meaningful step, a grain size to reality, below which the smooth picture simply stops being true. And to feel what that means, I want to take you down, away from the world of ovens and lamps, into the place where the graininess lives. Look at a single glowing ember in a dying fire. To your eye, it pours out a smooth, steady, continuous wash of warm red light. Now imagine you could slow down time and shrink your view, sinking past the surface of the ember, down into the lattice of its atoms, each one trembling with heat. You hover beside a single atom, watching, and what you see is not a smooth outflow of light at all. You see the atom hold its energy, hold it, and then release it all at once in a single tiny flash, one packet, one quantum, and then nothing, and then another. The light is not a river, it is rain. Countless separate drops, each one indivisible, each one carrying exactly its frequency, times Planck's constant, no more and no less. Pull your view back up toward the everyday world, and the rain blurs into a stream again, the drops so small and so numerous that the warmth on your face feels perfectly smooth. But you have seen the truth now. Underneath the seamless glow, the universe is counting out light one grain at a time. The smoothness was the illusion. The grains were always there. Planck simply found the seam where they show through. I want to slow down here and let you sit with how total this reversal really is, because it is easy to nod along to the word discreteness without feeling the weight of it. For the whole history of human thought before the quantum, the smoothness of the world was not just an assumption. It was so obvious that it barely counted as an assumption at all. Of course, you could always take a smaller step. Of course, motion was continuous. Of course, between any two amounts of energy there was always a third, halfway between. To deny this would have seemed like denying that 2 and 2 make 4. The continuity of nature was woven so tightly into common sense that for thousands of years no one even thought to question it, because it did not look like a claim about the world. It looked like the world. And then a tiny constant, dragged into physics by a man who did not want it there, quietly informed us that all of it was wrong. Not wrong in the everyday sense, where the smoothness is a near-perfect approximation, but wrong at the foundation, where it counts. There is a smallest step. There are amounts of energy with nothing in between them. The river of nature has a finest drop after all. To absorb this fully is to feel the floor of ordinary intuition tilt, because it means that the most basic picture we carry of how things change, a picture so basic we never chose it, is a kind of illusion produced by the smallness of a number. The world we see is real, but it is not fundamental. Underneath the seamless surface, reality is doing something our senses were never built to perceive, counting out existence in steps too fine to feel. That alone would have been revolutionary, but discreteness was only the first gift, and not the most frightening one. The deeper consequence, the one that would have horrified Planck most of all, took another 25 years to arrive in full, and it struck directly at the thing he held most sacred, the lawful, deterministic, predictable nature of the universe. For the quantum did not only make energy grainy, it made the future uncertain. In the classical world Planck loved, certainty was, in principle, total. If you knew the exact position and the exact motion of every particle in a system, you could calculate its entire future and its entire past with perfect precision. The universe was a film already shot, and complete knowledge of one frame let you read off every other frame. This was not just a hope. It was the working assumption beneath all of physics, the very meaning of a law of nature. But buried in the quantum, waiting, was a principle that made this dream impossible forever. In 1927, a young physicist named Werner Heisenberg would prove that you cannot, even in principle, know both the exact position and the exact motion of a particle at the same time. The more precisely you pin down where something is, the more hopelessly uncertain its motion becomes, and the reverse. And this is not a limit of our instruments, not a temporary clumsiness we might engineer our way around. It is a property of reality itself. The particle does not have a definite position and a definite motion that we merely fail to measure. It does not possess both at once. The universe, at its root, withholds. Feel the size of that, because it is the true horror Planck had glimpsed from a distance. Before his constant, the universe was, in principle, completely knowable. After it, a portion of reality is permanently structurally hidden, not by our ignorance, but by the design of nature. There is a flaw to certainty, and the height of that flaw is set by Planck's constant, the very number he tried to make vanish. Had the constant been 0, the flaw would have dropped away, and perfect knowledge would have been possible again. But the constant is not 0. It is small, but it is real, and its reality means that the universe keeps a part of itself forever beyond our reach. Something was taken from the world when Planck found his constant, and it can never be given back. The dream of a fully knowable cosmos, the dream that had guided physics since Newton, died in that glowing cavity. Though no one at the December lecture heard it fall, it helps to name exactly what was lost because the loss is precise, not vague. Before the quantum, physicists held what is sometimes called the clockwork picture of the universe, and its boldest expression was a thought experiment about a hypothetical intelligence great enough to know the position and motion of every particle in existence at a single instant. Such a mind, the old physics declared, could calculate the entire future and the entire past with perfect certainty, because the present completely determined everything that would ever happen. Nothing was open, nothing was undecided. The future was already written in the configuration of the present, waiting only to be read. This was not a fringe idea. It was the mainstream understanding of what the laws of physics implied, the very meaning of a deterministic universe. The quantum took that imagined mind and proved it impossible, not merely impractical, but impossible in principle. For that all-knowing intelligence to do its work, it would need the exact position and the exact motion of every particle at once, and the uncertainty principle says that those two quantities cannot both have definite values at the same time. The information the clockwork required does not exist to be known, because the universe does not hold it. The grand calculation can never be performed, not because no mind is large enough, but because the numbers it would need are not there. With that, the most ambitious dream physics ever entertained, the dream of total predictability, quietly closed. The future, it turned out, is not fully written. The universe keeps some of its pages blank until the moment they are lived. And there is more, a final strangeness that follows close behind. The quantum suggests in its standard interpretation that particles do not even possess definite properties until they are measured. Before you look, a particle is not secretly here or there. It exists in a haze of possibilities, a blurred superposition of every outcome at once, and only the act of measurement forces it to settle into a single answer. The question of how and why that settling happens, of what counts as a measurement and why looking should change anything, is called the measurement problem, and it remains genuinely unsolved to this day. More than a century after Planck's lecture, the finest physicists alive still argue about what the quantum actually means, about whether reality is definite before we observe it, about whether there is one world or countless branching ones. The mathematics works flawlessly. The predictions are the most precisely confirmed in all of science, and yet what it is telling us about the nature of reality is still, after all this time, a mystery that no one has resolved. This is what Planck had actually found. Not a better formula for light bulbs. He had found the end of the continuous universe, the end of perfect knowledge, and the beginning of a reality that refuses to fully exist until it is looked at. He had reached for the most solid ground in physics and discovered that there is no solid ground, that beneath the smooth and certain world there is something granular, probabilistic, and partly unknowable, holding everything up. No wonder he could not bear it. No wonder he spent a decade trying to send it back. He had wanted to find the bedrock of reality, and instead he had found the place where reality dissolves into possibility. He had wanted certainty, and he had handed the human race a permanent structural uncertainty that we have never escaped, and if the quantum is right, never will. The man had set out to defend the clockwork universe. He ended by proving that the clock was never really there. And the cruelest part, the part still waiting in his story, is that the universe was not finished taking things from him. It had already taken his certainty. Before the end, it would take far more than that. Part 10. The Cost of Being Right. It is tempting to imagine that a man who reshaped the foundations of physics must have been rewarded by life, that the universe owes its great discoverers some measure of peace in exchange for what they give it. Planck's life is the harshest possible answer to that hope. Few people in the history of science were asked to pay so much, and the sheer accumulation of his losses gives his story a weight that goes far beyond physics. To understand the man who tried to bury the quantum, you have to sit with everything the world took from him while he carried it. The losses came in waves across the decades. His first wife, the mother of his 4 children, died in 1909 after more than 20 years of marriage, leaving him a widower in the middle of his life. Then came the First World War, and with it the loss of his eldest son Karl, killed in action at Verdun in 1916, one of the war's countless young men fed into one of its most senseless battles, and the war was not done with his family. His 2 daughters, twin sisters named Greta and Emma, each died in the act of giving birth, within a few years of each other, one in 1917 and the other in 1919. A father who outlives one child knows a grief most people are spared. Planck outlived 3 of his 4 children before he was old, and he did it while continuing every day to do the careful, patient work of physics, holding the discipline together in a country falling apart around him. He stayed in Germany through its darkest years, through the rise of the Nazi regime in the 1930s, when the science he had devoted his life to was being twisted and gutted, when Jewish colleagues and friends, including Einstein, were driven out of the country or worse. Planck was an old man by then, in his 70s, and he made a fateful choice. He decided to remain, believing he could do more good by staying and trying to preserve what he could of German science than by leaving. It was a decision that has been debated ever since. An old conservative patriot trying to shield the institutions he loved from a barbarism he despised but could not stop. He even met with Hitler personally to plead, unsuccessfully, on behalf of Jewish scientists. He watched the world he had known be poisoned, and he stayed, and he endured. And then the universe took the last thing it could take. Planck had a surviving son, Erwin, the same son who, as a boy, had reportedly walked with his father while Planck confided that he had made a discovery as great as Newton's. Erwin grew into a man his father loved deeply, perhaps the person closest to him in his final years. In 1944, Erwin was implicated in the failed plot to assassinate Hitler, the conspiracy of July of that year. He was arrested by the Gestapo, and in January of 1945, with the war all but lost and the regime collapsing, Erwin Planck was executed. The old man, who had already buried a wife and 3 children, who had given the world the quantum and spent his life wrestling with its meaning, now lost his last son to the cruelty of his own country in the final pointless months of the war. It is said that something in Planck broke then that never healed, that the will to live nearly left him entirely. He was in his late 80s. He had given everything, and everything had been taken. It would be easy to let the sheer scale of his suffering turn Planck into a symbol, a figure of tragedy too large to feel as a person. But the truth is that he endured it as any of us would, one ordinary day after another, getting up, doing his work, carrying his losses quietly, because there was nothing else to be done with them. He did not stop being a physicist when his children died. He did not abandon his careful habits or his patient rigour. He kept lecturing, kept corresponding, kept tending the institutions of science through years when the world seemed determined to burn them down. There is a kind of strength in that which has nothing to do with genius, the plain human strength of continuing, of refusing to let grief erase the small daily acts that hold a life together. And through all of it, the quantum was always there. The strange truth he had uncovered, now grown into a whole new physics that the young spoke fluently, and that he himself had never fully embraced. There is a particular loneliness in outliving not only the people you loved, but also the certainties you were raised on, in finding yourself an old man in a universe that no longer works the way you were promised it would. Planck lived in that loneliness with remarkable grace. He never grew bitter toward the science itself, never denounced the revolution he had reluctantly begun. He accepted in the end that the world was stranger than he had wanted, just as he had accepted every other loss, with sorrow and with dignity, and without ever pretending the loss was not real. He had wanted a lawful, orderly, comprehensible universe. He got a granular and uncertain one, and he carried that disappointment the way he carried all the others, quietly, to the end. There is a line of Planck's, written in his scientific autobiography near the end of his life, that has become one of the most quoted observations in all of science, and it carries a different flavour when you know the man who wrote it. He observed that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with the idea from the beginning. People often quote this cynically, as a wry comment on the stubbornness of old scientists. But coming from Planck, it is something deeper and sadder. He was describing his own life. He had been, in his way, one of those opponents, resisting the full meaning of his own discovery for years, and he had lived long enough to watch the quantum win not by persuading the old guard, but by outlasting them, by becoming the native language of the young. He had seen from the inside exactly how a revolution conquers a mind, which is to say slowly, incompletely, and often only by waiting for that mind to pass away. What makes Planck's version of this so poignant is that he was talking about the triumph of his own idea, an idea he had given the world and then fought, an idea that had cost him his comfort and his certainty, and that had now outlived almost everyone he loved. He did not get to enjoy a tidy reconciliation. He got to grow old inside the strange truth he had uncovered, watching it spread and harden into the foundation of a new physics he never fully felt at home in. He had opened the door, and the world had walked through it, and built a whole new house on the other side, and Planck stood in that house as an honoured, grieving guest, recognised by everyone as the man who had unlocked it, and at home in none of its rooms. He died in October of 1947, at the age of 89, having outlived nearly everyone and nearly everything that had given his life its early shape. The great scientific society of his nation was renamed in his honour, and it carries his name still, one of the most respected research organisations on Earth. The constant he introduced in desperation now sits at the very centre of physics, and as of 2019, it has even been used to define the kilogram itself, so that every measurement of mass anywhere in the world now traces back, invisibly, to Planck's number. The man who tried for 10 years to make his constant disappear ended with that constant stamped into the definition of weight, woven so deeply into the structure of science that it can never be removed. Stop and let that final irony settle, because it is almost too perfect to be real. For 10 years, Planck laboured to make his constant vanish, to prove it was a temporary fiction that a deeper physics would erase, and the universe answered that decade of effort by doing the exact opposite of what he wished. It took his number and made it permanent in the most literal way imaginable, building it into the very definition of mass, so that today, every time anything anywhere is weighed, from a feather to a star measured by its gravity, the measurement traces back through a chain of definitions to Planck's constant. The thing he tried hardest to abolish became one of the most unabolishable quantities in all of science. There is a strange comfort in that, even amid all the loss, a sense that the universe has a way of honouring the truth despite the wishes of the people who find it. Planck did not want the quantum, and he got it anyway. And then he got it carved into the foundations of measurement itself, a monument he never asked for to a discovery he tried to refuse. He had wanted his name attached to the defence of classical physics. Instead, it is attached to the constant that ended it, to the society that bears his name, to the length and time and mass at the bottom of reality. He could not bury his discovery. In the end, his discovery enshrined him. The universe took almost everything from Max Planck, but it gave him this, an immortality built entirely out of the one truth he spent his life wishing were not true. There is a terrible kind of justice in that, and a terrible kind of mercy too. Planck wanted, above all else, for the universe to be lawful, orderly, and built on solid foundations. He spent his life in service of that vision, and the universe repaid him by making him the man who proved it false, and then by taking from him almost everyone he loved, and then, at the very end, by carving his name into the bedrock of the science he had tried to protect. He got his place in the foundations, he just did not get the foundations he wanted. And the thing he found, the thing he tried so hard to bury, was still down there, still waiting, ready to become the ground beneath everything the modern world would build. The door he had opened was not going to close. It was never going to close again. Part 11. The door that will not close. So let us return at the end to where this all began, to a small bright hole in the side of a heated oven, glowing with the pure colour of its own warmth. That glow in the oven was the seam in the universe, the one place where the graininess of reality leaked through into an experiment careful enough to catch it. Everything we have travelled through tonight, the desperate guess, the decade of retreat, Einstein's grains of light, the death of certainty, the long suffering of a single human life, all of it flowed out of that humble little opening. And the strangest, quietest truth of the whole story is that the glow in the oven was never special. It was only the place where someone finally looked closely enough, because that same glow is everywhere. It is in the filament of the lamp beside you, counting out its light one quantum at a time. It is in the embers of every fire that has ever warmed a human face, back through every hearth and every campfire to the first flames our ancestors ever kindled. It is in the surface of the sun, pouring out its radiation in discrete packets across 93 million miles of empty space to land, grain by grain, on your skin. It is in the faint, cold afterglow of the Big Bang itself, the oldest light in existence, which follows Planck's radiation law so perfectly that it stands as some of the strongest evidence we have for how the universe began. The quantum was never hiding in some exotic, distant corner of reality. It was in every warm and glowing thing in plain sight the whole time, whole. Planck did not travel to the edge of the cosmos to find it. He found it in a furnace because it was already in everything, waiting for a mind patient and honest enough to be cornered by it. And think now about that phrase Planck gave us, his own confession, an act of desperation. When we first heard it, it sounded like a man apologizing for a guess, embarrassed by the unprincipled way he had reached his formula. But stand here at the end of the story, and the phrase changes its meaning entirely. His desperation was not the desperation of a man who had stumbled into something trivial. It was the desperation of a man who had glimpsed, before anyone else, the true face of reality, and who understood, faster and more deeply than his contemporaries, that it would cost the universe its solid ground. He was not desperate because his method was sloppy. He was desperate because he could see where it led. The act of desperation was the act of a man staring through that little glowing hole and seeing, at the bottom of it, a world with no certainty in it, and reaching in anyway because the truth gave him no choice. His desperation was a kind of foresight wearing the mask of reluctance. For 10 years he tried to make it disappear. We have used that phrase again and again tonight, and now we can see it for what it truly was. He tried to make it disappear because some part of him already knew it could not be made to disappear, and that is precisely why he tried so hard. You do not spend a decade fighting a triviality. You spend a decade fighting the thing you are most afraid is true. Every failed derivation, every clever attempt to send the quantum back into the smooth classical world was a measure of how enormous he understood the discovery to be. His resistance was not blindness. It was the most eloquent possible testimony to the size of what he had found. The man fought hardest against the truth he saw most clearly, and his struggle is the proof of his vision, and the door he tried to close will not close. That is the final permanent fact of this story. Once the universe has shown you that it is granular, you cannot unsee the grains. Once it has shown you that certainty has a flaw, you cannot rebuild the dream of perfect knowledge. Once it has shown you that a particle may not be anywhere at all until you look, you cannot return to the comfortable world where everything quietly exists whether or not anyone is watching. Planck pushed against that door with everything he had for the rest of his life, and the door stayed open, and through it poured the entire modern world, every transistor, every laser, every medical scanner, every solar cell, every computer chip in every device you have ever held, all of it built on the quantum he tried to bury. We live, all of us, on the far side of the door he could not close. So let me leave you, as the fire burns down, with the question the whole story has been circling, the one Planck himself never fully escaped. Picture again that haze of possibility, the particle that has no definite place until the moment it is measured, the universe that seems to hold its outcomes in suspension until something looks. We still do not know, after more than a century, whether the world is truly definite when no one is observing it, or whether reality, at its deepest level, waits. We do not know whether the moon is really there in some complete and certain sense when nobody looks at it, or whether existence itself is grainier and stranger than even Planck dared to fear. The mathematics is flawless, the mystery underneath it is total, and every answer we have ever built rests on a question that the father of the quantum spent his whole life refusing to look at and could never quite look away from. Consider, before we close, what it means that the most successful theory in the history of science is also the one we understand least. Quantum physics makes predictions of staggering accuracy. There are quantities it forecasts that match experiment to more decimal places than almost anything else humans have ever measured. Agreements so precise they are like predicting the distance from one coast of a continent to the other, and being correct to within the width of a single hair. By every practical test, the theory is not just true, but the truest thing we have ever built. And yet, when you ask what it actually means, what kind of world it is describing, the most honest physicists alive will tell you that they do not fully know. We have a flawless map and no agreement about the territory it depicts. We can use the quantum to land probes on distant worlds and to fill your pocket with computing power, and we still cannot say with confidence what is really happening underneath. That gap between the perfection of the mathematics and the mystery of its meaning is the inheritance Planck left us, and it is a stranger and more wonderful gift than the comfortable certainty he wished he could have given instead. He wanted to hand the human race a finished, knowable universe, the cathedral complete down to its foundations. Instead, he handed us a doorway and an unanswered question, an invitation to keep looking that has never expired. More than a century of the most brilliant minds our species has produced have walked through that doorway, and the question on the other side is still open, still waiting, still as alive as it was on that December evening in Berlin. Planck did not give us answers. He gave us the one thing more durable than any answer, which is a mystery large enough to last. He went searching for the most solid ground in all of physics. He found the exact place where the ground gives way. and the rest of us have been living on that beautiful, uncertain edge ever since, in a universe that counts its light in grains, keeps a portion of itself forever hidden, and may not fully decide what is real until the moment we open our eyes and look. Max Planck saw all of that, a little before the rest of us, glowing faintly in the mouth of a furnace. And he was right to be afraid, and he was right to look anyway. Tonight, somewhere above you, the same grainy light is falling from every star in the sky, one quantum at a time, the way it always has, carrying the secret he could not bury, the secret that is simply the way the universe has always been.